Okay, we're continuing on. Chapter 13 is where we left off, and we started talking about gases, and we ran through a bunch of gas laws last time. We had P1 V1 equals P2 V2. That's our Boyle's law. We had our V1 T1 equals V2 T2, a little Charles law action, along with Guy Lussig's, which is P1 T1 is equal to P2 T2. Right, little Charles. Remember, as we also talked about, temperature does need to be in Kelvin. In terms of pressures and volumes, really, they could be any unit that you want as long as they are the same on both sides. We also saw our friend Avogadro and his law, V1 over N1 equals V2 over N2, N being moles in this case. We also talked about PV equals nRT, which is the ideal gas law, and also the most restricted out of all the gas laws in terms of units. Pressure has to be in atmospheres when you use this. Volume needs to be in liters. Moles should be in moles. And temperature, like any other gas law, needs to be in Kelvin. And really, all that's because of R, which is the gas constant. And again, this is a constant value, as we talked about last time. It's a value that you always have, but very commonly never given to a problem. So they just kind of assume that you know that you do have that value available to you. It also, when you look at the units, there's pretty much all the other units that everybody needs to be in so that everything properly cancels out. Yeah. Yeah. That would be the next one we're going to talk about right here in just a sec. And we'll talk about, we also did talk about before there STP, which is standard temperature and pressure. That gives you a pressure of 1 atmosphere and also a temperature of 273 Kelvin. So remember that if they do say STP, they are technically giving you both a pressure and a temperature value, and those would be the ones that you use. I'm sorry, I'm so used to it, but here they do want you to use the 0.15 version of that 273.15. Remember that if you are at STP, there is a conversion factor that you could use that will actually allow you to not have to use the ideal gas law, and that is 1 mole of any gas will equal 22.414 liters. As we talked about last time, you can only use that if you're at STP. If you're not at STP, then you should not use that at all. You could always use the ideal gas law under any conditions. So it's like a universal sort of gas law. Doesn't matter the conditions. You can always go into the ideal gas law and use it to solve for something. We finished up on, which was the question there, which was sometimes referred to as the combined gas law, P1 V1 over T1 equals P2 V2 over T2. And that, once again, is the combined gas law. And as was mentioned a second ago, this is the one I mentioned that if you want to remember it in that version, like I boxed, or sometimes this version here where it still has the moles in it. This is a really good one to remember because, frankly, you could get all the gas laws up here pretty much from it. Again, what you do is just scratch out whatever is held constant or whatever is really not mentioned in the problem. So again, if you weren't given any type of moles or temperature, you just scratch it out and you got Boyle's law. If you, again, use the numbers right there. If you were given any pressure or moles, you could just scratch those out. And again, you would have Charles' law here. And that's just a way that you could kind of use that equation really to get to all of them. Whatever's not given to you or not mentioned or held constant, you just kind of scratch it out and you'll get it. So as I said last time, if you pretty much remember this one, and you remember really the ideal gas law, which is pretty much like this one here, in a sense, you will be able to really get to sort of all the gas laws that you would need very quickly. The other thing we talked about obviously was units, and 1 atmosphere is equal to 760 torr, and that equals 760 millimeters of mercury. And again, those are the big three sort of units that you come across most here in chemistry. Any questions on any of those there? All right, so I think we didn't do the example, so let's do it. Consider a sample of oxygen gas at 27 degrees Celsius, has a volume of 9.55 liters, a pressure 2.97. The pressure goes 825 and it's heated to 125. What will be the new volume? So let's take a look. Once again, as you talked about, sometimes it's good to just pull out the information. So here we have a temperature of 27 degrees Celsius. We got a volume of 9.55 liters, and we got a pressure there of 297. We have another pressure of 825, and we have a temperature of 125, and we are looking for a volume. So once again, if you're not sure what gas law to choose, you should hopefully be able to kind of see the combined gas law kind of sitting in front of you there with just everything that you labeled. We just got to check some units. Our atmospheres are good on both sides here, but like normal, we do need to convert our temperature into Kelvin. That's almost like a non-brainer type thing. Just always do it at the beginning here. And we will get that there. It's like 300.15 and 398 here on this side, looks like. 5 plus 273. All right, so now that we have everybody in the proper units, we'll use our combined gas law here, P1 V1 over T1 equals P2 V2 over T2. Here we are obviously looking to solve for V2. A reminder, a quick way to rearrange, right, is put everybody in the opposite location. So that guy's going to go up and this guy is going to go down, basically, by multiplying and dividing is essentially what we're doing there. So that's going to give us P1 V1 T2 divided by T1 P2. It's going to equal our V2. So now we can put everybody in the correct spot. We'll go with our P1, which is 2.97 atmospheres, our V1, which is 9.55 liters, and our T2, which is 398.15 Kelvin, divided by our T1, which is 300.15 Kelvin, and our P2, which is 8.25 atmospheres. Atmospheres will cancel, Kelvin will cancel. Gonna leave us units of liters all left over, which is good, since we're looking for a volume, and that volume here looks like it will be something with some numbers, I imagine. 8.25, 4.56 liters in this case. Any question on that calculation? So I would say probably for a lot of people, this one gives them a hard time rearranging. So again, if rearranging these equations are difficult for you, make sure you do take some time to know how to properly do it. But really just kind of opposite location as you go across the equal sign is pretty much a quick way to do that. And you should usually always be right. Any questions on that? Obviously, whatever you're solving for needs to be up on top, though. Yeah, so it's got to be up on top. All right. Then let's talk about stoichiometry that involves gases. And really, stoichiometry that involves gases are pretty much the same kind of steps. So you want to make sure you balance your equation. You want to convert to moles. And you still want to make sure that you determine whether or not you're dealing with a limiting reagent problem. And if you are, you still need to solve it kind of the same way as we did other ones. But if not, it might just be a basic stoichiometry problem, which a lot of them are. At that point, you could then go to your mole to mole relationship. And lastly, you could do your moles into some other unit. Now, the main difference here with stoichiometry that involves gases is somewhere along the way, a little PV equals nRT action is usually going to be used. I would say a lot of times at the very end, volume is what you're looking for. So a lot of times you may go into the ideal gas law and solve for volume. I would say if you use this guy early on, it would come right about here, and you would solve for moles, and then that would equal PV over RT. So those are two common places where you just sort of insert the ideal gas law. Other than that, everything in the middle there is sort of the same as a normal stoichiometry problem. Again, just got to make sure it's not a limiting reagent, and a lot of times it probably won't be, but you really just follow the same steps. Sometimes you may use them in both places. Sometimes you may just use the ideal gas law at the end. So it does sort of vary and depend on the problem, but definitely a lot of times on that very last step, you're going to use probably the ideal gas law to solve it, or really some other gas law as well is possible. You could use a combined gas law, for example, or something like that. But a lot of times it's going to be usually the ideal gas law. Any questions on that there? So let's take a look here and sort of see, consider this reaction. And we were looking for what volume hydrogen gas at 27 degrees Celsius and 1.25 atmospheres is required to react with 5.65 grams of phosphorus. So a couple of things here. We are looking for hydrogen, which is a gas. So that makes me think I should maybe use my ideal gas law at some point. And I know that I do have a temperature of 27 degrees Celsius. I do have a pressure of 1.25 atmospheres. I'm looking for a volume. And remember that we always have R given to us, or not really given to us, but we know it, which is our liters, atmosphere, Kelvin, and mole. So that's pretty much all about the hydrogen. I can see that if I check off sort of my ideal gas law here, I have a pressure, I'm looking for a volume, I have T and I have R. The one thing that I'm missing in terms of hydrogen is the moles of hydrogen. And that's really where the stoichiometry is going to come into play. If I think about the other piece of information that's given to me, which is I have 5.65 grams of phosphorus, I can use that and the molar mass of phosphorus, which I will borrow here from the periodic table, 3097. Looks good. And that's where the stoichiometry can come into play. We have phosphorus that will allow us to get to hydrogen using stoichiometry. And at that point, that will be really the missing thing that we need there for our hydrogen. So starting with that, we're going to balance the equation, and it is balanced. So step number one's done. Step number two is we're going to convert to moles. And really the only thing that we can convert to moles with is the 5.65 grams of phosphorus. So using the molar mass there, we'll take very badly written today. Let's try this again. All right, we got our 5.65 grams of P4. We need the molar mass, obviously, of P4, which would be 4 times 3097 grams per mole from the periodic table. And that's going to get us 4 times 3097, 123.9. And that was our conversion factor, 123.9 grams per mole of phosphorus. The grams of phosphorus are going to cancel out. And if you get an answer at this point, 5.65 divided by 123.9, going to get us here 0.04560. And that is moles of phosphorus. Remember, though, that we actually need moles of the gas, so we could go into the gas law. So this is the stoichiometry part in the third step there, which is our mole-to-mole relationship. And we can see for every 1 mole of P4, we get 6 moles of H2. So that is what we will do next. 1 mole of P4 gives us 6 moles of H2. And if we put that in, we're going to times this by 6, give us 0.2736. That is now the missing piece that we needed to use the ideal gas law. So we can use now for our fourth step here, our PV equals nRT. We're going to solve for volume, which is nRT over P. Now we do need to do one thing, which is we need to convert our temperature into Kelvin. So that's going to be 27 plus 273.15, going to be 300.15. And now we have everything that we need. So using the moles we just calculated, using our gas constant, which we always have, our temperature converted into Kelvin, all divided by our pressure, which was 1.25 atmospheres. Moles will cancel, Kelvin will cancel, atmospheres will cancel, going to leave us volume. And that means in this case here, we're looking at about 5.39 liters here of H2. Questions on those steps? Really, again, the same 4 steps that we do in a stoichiometry problem. Just here at the end, we're going to put it into the ideal gas law. And much like a normal stoichiometry problem, you can combine these steps here and just do it without getting an answer, obviously in between if you wanted to. Any questions on that one there? All right. Let's try another one here. Let's try this one here, which is the experiment you did the other day. Magnesium reacts with hydrochloric acid gas. Calculate the volume of hydrogen gas produced at STP if we reacted 5 grams of magnesium. Magnesium 2431, I believe. So give that a go, see what you come up with. Okay, let's take a look. So this is pretty much the experiment we did last week, and the calculation pretty much similar here for your theoretical yield, for example. We want to calculate the volume of hydrogen gas in this case at STP. Remember, when you see STP, that is a temperature value of 273.15 Kelvin. That's also a pressure value of 1 atmosphere. So we do have pressure and temperature. Obviously, we're looking for a volume. And again, we always have R given to us here. So we can definitely use our ideal gas law in this situation, PV equals nRT. We have our pressure, our temperature, our R. We are looking for a volume. So once again here, we are missing the moles of hydrogen. Obviously, this is all about hydrogen, which is the gas in this case. So we do need to use stoichiometry to get us to the moles of hydrogen. And that's the other piece of information here. It also tells us in this problem it's excess amount of HCl, like in your experiment, which means that magnesium is the limiting reagent, so we don't have to worry about that aspect of it. So here we do have the equation is balanced. We do need to convert this guy into moles. So that's what we'll do here. And again, we have the molar mass given to us. So we'll take our 5 grams of magnesium. We'll use the molar mass from the periodic table, 2431 grams per mole of magnesium. And that's going to give us here 0.2057, we'll call it, moles of magnesium. Once again, we don't need moles of magnesium, but we do need moles of hydrogen. So this is going to be the stoichiometry part of the calculation, which is the relationship between those. And we can see that for every 1 mole of magnesium, we get 1 mole of H2. That makes the math not too bad here. So we'll take our moles of magnesium. We'll do our stoichiometry to convert it into hydrogen. That's going to give us 0.2057 moles of hydrogen. So now that we have that, we now have really the missing piece that we need to solve for this. So in this case, we're going to solve for volume, which is nRT over P. Our moles we just calculated, 0.2057. Our R, which is 0.08206. and our temperature, which is 273.15 Kelvin, all divided by our pressure, which is 1 atmosphere. Atmospheres cancel, moles cancel, Kelvin cancels, leaves us once again just liters left over, and that's going to get us here. It looks like 4.61 liters in this particular case of hydrogen. That would be in this case a theoretical yield, as hydrogen obviously is a product. So that would be like our theoretical yield here. And again, the similar calculation, pretty identical calculation you're supposed to do for the lab. Question on that there. Is there another way I could have solved this? And as we talked about, I think last week, there is another way you could have solved this because we are at STP. We know that when we're at STP, 1 mole of any gas will equal 22.414 liters. That means I could actually just have picked up right about here and got my moles of hydrogen. And in this case, because we are at STP, I could use that relationship of 1 mole, 22.414 liters, and you will end up at the same spot. So this is a place where you could use that conversion because it's at STP, and you would not need to use the ideal gas law. But also a good reminder that if you don't remember that or not sure you should do that, you could always use the ideal gas law in any situation. So again, the ideal gas law is sort of a universal formula that can be used in any situation: STP, non-STP, normal conditions, whatever conditions it may be. Any questions on that there? All right. I think we will lay it up there, actually. Yeah. Yeah.